Hello, physics students. Let's consider what we mean by the conservation of momentum. Now, we'll start with a statement that describes this conservation. In any closed and isolated system, momentum is always conserved. Now, that's a very powerful statement. Whenever in physics we say something is always true. But notice the two conditions there. We're talking about closed and isolated. What do we mean by closed and isolated? So by closed, we mean that no mass enters or leaves the system. That is, whatever objects are interacting, I need to consider all the mass of all the objects before they interact and after they interact. Now, what we mean by isolated means that there are no external forces. Acting on the system. Now, that is external forces, such as maybe friction, or maybe the objects rolling downhill and gravity are acting on them. But if I can isolate the system and have no external forces, then momentum is conserved. Now, this doesn't apply to internal forces. Imagine that two carts have a compressed spring between them. When the spring releases, the carts will move away. That action of the spring does not change the momentum of the system. That is, before the spring releases, the momentum of the system would be zero. Afterwards, the momentum would still add to zero because I have two vectors in opposite directions. And so that is a very important consideration. Internal forces are okay. External forces are not. Now, a typical example of this is we consider a cartoon bomb exploding. All right, so in this before picture, I have the bomb which has some mass and it has no velocity. So my momentum before is equal to 0 kilograms meters per second because there's no velocity and so there's no momentum. Now, a bomb can experience very strong internal forces. When the bomb explodes, the force of the expanding gases are internal to the system, and it's going to act on these masses. But my final momentum is still 0 because if I add up the mass of one piece of the bomb times its velocity plus the mass of the other side of the bomb times its velocity, I submit to you that these are going to equal to 0. Now I'm putting the primes on them to represent that this is after the event, after the explosion. Now, how can these things add up to 0? Well, they add up to 0 because these are vector quantities, which means I have to take into consideration their directions. So this first piece here is going to the left. So what I'm telling you is this mass times this velocity to the left. If I added to it the other piece of mass times the velocity to the right, these will always add up to 0 because that was what the initial momentum was. Now, the masses and velocities could be different. They don't have to be equal in quantity, but if this mass is smaller, that velocity needs to be larger, and if that mass is larger, that velocity needs to be smaller in order for the vectors to add up to 0. So, and this would hold true if the bomb had some initial velocity. If the bomb was initially moving to the right, then if I calculated the final momentum, it would come up with a momentum pointing to the right, a positive momentum. So let's work an example problem. And here, when we're doing conservation problems, it's incredibly important to keep track of all the objects in the collision as well as choose variables that make sense. Rushing the numbers in these problems is a big way to make a mistake because there's too much information to keep track of. So let's look at a typical example. So the example here is Sally Squirrel has a mass of 5 kilograms and is riding a light cart east at 6 meters per second. A light cart is physics speak for we don't have to worry about the mass of the cart. She collides with Harry Hedgehog, who has a mass of 10 kilograms and is resting in a light cart. That means Harry is not moving. After the collision, Sally is moving west at 2 meters per second. How fast is Harry moving after the collision, and what energy is lost in the collision? All right, well, when you're doing these problems, the first thing that you need to do is sketch a before and after picture. In my before picture, I have Sally moving with some initial velocity that I can call Vs, and she's going to collide with Harry, who has initial velocity equal to 0. In my after picture, Sally is now moving in the opposite direction. So this is the velocity of Sally going after the collision, but Harry is now moving. So the name of the game is I need to write a momentum equation for the system before the collision. I need to write a momentum equation for the system after the collision. And because momentum is conserved, I can then set those equations equal. Now, I, of course, have a better picture thanks to the miracle of clip art. So let's take a look at it. So here is our basic situation. I have Sally moving to the right. He's going to collide with Harry, who has no initial velocity. So here is the velocity of Harry before the collision. Now, this is the velocity of Sally here after the collision. And I said that this was equal to 2 meters per second. But because it's moving west, I need to put a negative there. Now, be careful with any vector equation that you don't accidentally put the negative signs in twice. Now with Harry, technically I don't really know which way Harry is going to be moving. I can pretty much guess that it has to be right in order to conserve my momentum, but I just will assign a velocity vector to Harry, and this is the velocity of Harry after the collision. Now, the nice thing about momentum problems, it doesn't really matter what direction you choose for the missing velocity. If you choose the direction correctly, when you do your math, you'll get a positive answer for that velocity. But if you choose incorrectly, you'll still get an answer, but it'll be negative. When doing a momentum problem, if you find the velocity, and if you get a negative answer for the velocity you chose, it just means you chose the direction wrong and should go back and fix it. So let's set up our equations. So in the before picture, I have two objects, and even though Harry's not moving, I have to consider Harry because he's part of the system. And therefore, I'm going to write my initial momentum equation. My initial momentum equation is the mass of Sally, the velocity of Sally, plus the mass of Harry times the velocity of Harry. Now, I'm putting vector hats on my velocity vectors to let me know that I haven't put any signs in yet. Now I'll continue on. I'll put in the signs. So I have the mass of Sally, the velocity of Sally. That's positive, so I'm taking off the vector hat. Plus the mass of Harry times 0 velocity. So that will become 0. And so my initial momentum equation is simply mass of Sally times velocity of Sally. Now let's look at the after picture. In the after picture, I have the mass of Sally times velocity of Sally after the collision, plus the mass of Harry times the velocity of Harry after the collision. And again, I'm not worrying about signs. I'm just getting my momentum equations lined up. I have the vector hats to remind me that I need to put the directions in now. Now, by the way, if they ended up sticking together, that is called a perfectly inelastic collision. You are almost always going to lose energy in a collision. Not necessarily. So in physics, an inelastic collision means you lose energy. In elastic collisions, energy is conserved. That is, there is no change. Now, if objects collide and stick together, then you are guaranteed not only to have an elastic collision, but you're going to maximize energy loss, and that's called a perfectly inelastic collision. Here, the objects don't stick together. If they did stick together, I would put the masses together in parentheses and multiply by their common velocity, but that's why the picture is so important. So let's put in the signs here. So I know my final momentum equation is going to be minus the mass of Sally vs prime. And again, I put in the negative sign because she's moving left, plus the mass of Harry times the velocity of Harry prime. And I'm leaving that positive because I chose the direction to be to the right. Now, I could have put the direction to the left and then I would make this negative, but you would see that that direction would end up being wrong. Now, because momentum is conserved, because change in momentum of my system is going to be 0, I can set these two equations equal to each other. So I'm going to have that the mass of Sally times the velocity of Sally equals minus the mass of Sally times the velocity of Sally after the collision plus the mass of Harry times the velocity of Harry after the collision. Lots of things to keep track of. It's a good time to take an inventory. I know the mass of Sally, and that's not changing before and after collision. I know the mass of Harry. That's not changing. I know the velocity of Sally before the collision. I believe that was, let's put some information on this. Sally is 5 kilograms, moving at 6. Harry was 10 kilograms. And this velocity was at 6 meters per second. All right, so I know the velocity of Sally after collision. I do not know the velocity of Harry after collision, but there's only one unknown, so I am good to go. So, solving this, I'll get the mass of Sally times the velocity of Sally plus the mass of Sally times the velocity of Sally after the collision equals the mass of Harry times the velocity of Harry after the collision. So that means that the velocity of Harry after the collision will be equal to the mass of Sally, velocity of Sally, plus the mass of Sally, velocity of Sally afterwards, divided by the mass of Henry. I can clean this up a little bit by taking a look at by factoring out the mass of Sally. You don't have to. You could put in the numbers at this point. I like saving myself some calculator time. So that's going to be the mass of Sally was 5 kilograms times Sally was, that's going to be 6 plus 2 meters per second. And then Harry was 10 kilograms. So 6 plus 2 is 8. 8 times 5 is 40. 40 divided by 10 is after the collision. Harry is moving at 4 meters per second. And is to the right because I chose to the right and my answer worked out to be positive, so I chose correctly. Now let's talk about the change of energy in this collision. Change of energy is a bit of work because you have every object that's moving has kinetic energy. So if we go back up to the system, I see initially that Sally has kinetic energy, but Harry doesn't at the beginning. Afterwards, they both have kinetic energy. So I need to calculate in the after picture the kinetic energy for both objects and in the before picture only for Sally. I already have kinetic energy here, so it's going to be the final kinetic energy minus the initial kinetic energy. But this is for the system. So my final kinetic energy is going to be 1/2 the mass of Sally times Sally's velocity after the collision squared, plus 1/2 the mass of Henry times the velocity of Henry after the collision squared. And so you see there's lots of information to keep track of, hence the primes instead of the F's. But this will be equal to 1/2 5 kilograms times that's 6 meters per second squared. That's 2 meters per second squared. This is after the collision, not before. And notice I didn't worry about the negative sign because we square it and there is no direction in energy. It's a scalar, so it's just 2 meters per second squared. Plus, Harry was 1/2 times 10 kilograms times afterwards he was going at 4 meters per second squared. All right, so that's 2 squared is 4 times 5 is 20. 20 divided by 2, this is 10 joules here. 4 squared is 16 times 10 is 160. Half of that is 80 joules. Okay, so the total final kinetic energy, adding these two energies up, is equal to 90 joules. Well, that's the situation after the collision, so now we need to figure out the energy before the collision. Well, before the collision, that's going to be 1/2 mass of Sally, velocity of Sally squared, plus 1/2 mass of Henry, but that's 0 squared because Henry wasn't moving initially, so that piece is gone. So this is going to be 1/2 Sally's mass, which is 5 kilograms, times her velocity at the beginning, which was 6 meters per second, but that's squared. Now, so 6 squared is 36. 36 times 5 is 150. That's 180. A half 180 is also 90 joules. So if I go to calculate the change of energy here, that is the final kinetic minus the initial kinetic. That's going to be 90 minus 90. Or this is a change of energy of 0 joules. Now, this is known as an elastic collision. Pretty unusual. It's just blind luck. I chose these numbers fairly at random. I didn't put much forethought into them. And I'm actually lucky that the change of energy came out to be 0 and not an embarrassing positive number, because you can't gain energy in a collision. At best, you can lose no energy. But this is unusual. The more usual situation would be an inelastic collision. In an inelastic collision, the final energy will always be smaller than the initial energy. And your change of energy will be equal to a negative number. That's the more usual case. Now, if objects stick together, then you get what's known as a perfectly inelastic collision. That would be a situation where I would have some object collide with another object, and then afterwards they would stick together and roll off together. So my final momentum would be m plus m times v prime. Now, in this situation, you are guaranteed maximum energy loss. Just a handy thing to remember.